So welcome to chapter 10. So we're going back in regular order now. So we're going to talk about acids, bases, and salts. And I think one of the most surprising things is that water actually reacts with itself. So two water molecules can actually collide in solution. And of course, if they collide with an energy greater than the activation energy, they can react. And what they do is they actually form two ions, an H3O plus ion, which is called the hydronium ion, and an OH minus ion, which is called the hydroxide ion. So we've met those before, although it's been a long time. So this is hydronium. We will see that this is associated with acids. All acids are going to make this ion in solution or in water aqueous solutions. And OH minus is our hydroxide ion. So all bases are going to increase its concentration in solution. And this is sometimes called the self-ionization reaction. And it's called self-ionization because water reacts with itself and makes ions. So it makes these charged particles here, and we'll see that that allows the solution to conduct electricity. Sometimes we get a little bit lazy, and instead of writing the two water molecules that are colliding with each other, we can think of one water molecule essentially splitting apart. And so sometimes we write these simpler reactions. So H2O liquid breaks down and forms H plus and OH minus. And so this isn't quite as honest, to be honest. The H3O plus ion is much closer to reality, but you can imagine the H plus ion is pretty much the same thing. It's just it should normally be attached to a water molecule. And so that's just the hydrogen ion for short. And so sometimes we write hydrogen ions, sometimes we write hydronium ions. It's always better to write hydronium, but sometimes it's nice to be able to save half the waters and half the writing here and write it this way instead. So people have measured these concentrations, and it turns out that at 25 degrees C, which is very close to room temperature, it's probably a little warmer maybe than we'd be comfortable with, but the concentration of those ions, of the H plus ion and the OH minus ion, is exactly the same, and it's 1.0 times 10 to the minus 7, and that's capital M. That means molarity, which of course is moles per liter. So remember from the solution chapter, right, we write moles per liter normally as a capital M. And again, if you prefer, the much more precise way of writing it would be to write the H3O plus ion instead of the H plus concentration. And remember, we use those square brackets to represent the molar concentration just as a shorthand. Most of us are familiar with acidic, basic, and neutral solutions, but actually they're defined quite cleverly, and they're defined by comparing those two concentrations. So it actually, we'll meet the pH scale later, and some people define it in terms of pH, but this is actually always correct. The pH lower than 7 is acidic is not actually always correct, but this is always true. If the H plus concentration is bigger than the OH minus concentration, we say that this is an acidic solution. And if the H plus concentration is smaller than the OH minus concentration, we say that this is a basic solution. And when those concentrations are identical, then we say it's a neutral solution. And so for pure water is perfectly neutral. But as soon as we add something to the water, it can disturb the balance of those concentrations. And if it raises the H plus, right, remember the crocodile eats a bigger number. If it raises this concentration, it becomes an acid. And if it raises the OH minus concentration bigger than the H plus, it's a basic solution. Salts are ionic compounds, and salts normally don't change the acidity of the solution. So salts normally give rise to neutral solutions. This isn't exactly correct, but very approximately we can say ionic compounds like sodium chloride or potassium bromide, when we add them to water, they really don't change either the H plus or the OH minus concentration, so that leaves us with a neutral solution. Remember though, we met earlier the Arrhenius definitions of acids and bases, and the Arrhenius definition says that an acid is something that increases the H3O plus or the H plus concentration, whichever you prefer, and a base is something that increases the concentration of the hydroxide ion. And so we can see that's why you have an acidic solution. If you've got something that is pumping in protons or pumping in those hydronium ions, they're going to beat the OH minus concentration and make it acidic, and vice versa. So if you've got something like sodium hydroxide that basically dissociates and dissolves and make hydroxide ions, it's going to increase the concentration relative to H plus and make it what we call a basic solution. So acids are things that raise the H plus concentration. So they normally are molecules that contain the H plus ion as a cation. And we have example molecules, so something like HCl when dissolved in water, we call hydrochloric acid. This is the stomach acid. It's also toilet bowl cleaner, so technically if you do throw up in the toilet, you are going to do, you are eventually going to clean the toilet. And when it dissolves in water, it makes the H plus and the Cl minus ion. And it's this H plus ion that makes it an acid. Not everything, though, is as simple as this. So for instance, C2H3O2 is my favorite acid. This is acetic acid. And the reason it's my favorite acid is that a 3% solution in water we call vinegar, and I absolutely love to put vinegar on my French fries or my chips. Oh, it's so beautiful. And you might look at this substance here and you might think, well, it's actually got 4 hydrogens in, so this must be a really strong acid. It turns out it's not actually strong, but actually only one of those hydrogens actually will dissolve in solution and make it an acid. And the secret to all of this is that the acidic hydrogen is either written in first place or last place. And so we normally write the hydrogens that are acidic either at the front or the end. Conventionally, we write it at the front of this molecule, but those 3 hydrogens in the middle are not acidic at all. And the reason for that is that when it dissolves, it actually is in equilibrium, and it forms that H plus ion, which is what makes it an acid, but it also forms that acetate ion, and that acetate ion doesn't dissolve and make any more H plus ions, so it actually doesn't act as an acid at all at that point. You should be a little bit careful about tasting acids, but we're familiar with things like acetic acid and citric acid and vitamin C in that they taste, if I can spell taste, they taste very sour. And so I quite like that sour flavor, but if you're not into the vinegar kind of or the vitamin C kind of flavor, or if you don't like warheads, you're probably not going to enjoy this. The other interesting thing about acids is that they turn litmus, and litmus is an acid-base indicator, and in your locker you actually had 100 paper strips that were coated with litmus, and we used them in one of the very early labs, and you can basically dip them in a solution, or even better, add a drop of the solution to the paper, and litmus actually changes red in color when it's in contact with an acid. And so litmus turning red, or the flavor being sour, is the classic sign that you've got an acid. So bases are our yang to our acids that are our yin. So bases are the opposite of acids, and they typically contain the OH minus ion. And so, for instance, something like sodium hydroxide, which is commonly known as lye, when it dissolves in water, it breaks down and it makes the sodium ion, which we're not very interested in, but the hydroxide ion is what makes it a base. That makes it an Arrhenius base. Other things, so for instance, NH3, you will recognize as ammonia. It doesn't actually contain the hydroxide ion, but we'll see that it reacts with water in an equilibrium and it makes the hydroxide ion. So it makes the ammonium ion and the hydroxide ion, and that's what makes it a base. Bases are very well known for tasting bitter, and so if you like beer, if you like coffee, if you like tea, they all have that bitter flavor from the bases that are in them. Most of us are not huge fans of the bitter flavor. It's sort of one of those learnt tastes, like grapefruit. For many years I couldn't eat grapefruit, but in nature it serves a purpose because a lot of the bitter tasting things in the world are quite deadly poisonous. So if you go out into the world and you see those nice shiny red berries and you decide, yummy yummy, I think I might want to eat some of those berries, they have a very bitter flavor, and that's probably to save you from eating too many of them and poisoning yourself. The other really neat thing about bases is that they feel slippery. So they have that very slippery, slidey, soapy feel. And actually, the soapy is quite pertinent, actually, because when bases come in contact with your skin, they take the oils in your skin and they actually break them down and they turn them into soap. And so if you have a little bit of base on your fingers and you slide the fingers over one another, it will take your hand oils and greases and convert them into a very disgusting form of soap. But nonetheless, they're soapy, and soaps we know have that slippery, slimy kind of feeling. Just like acids, litmus also changes color in the presence of a base, and so litmus actually turns a very interesting blue color. And so we did one of those early labs, I think, where we tested, and we started with an acidic solution that turned litmus red, and we neutralized it by adding base, and eventually when we fully neutralized it and added 1 drop more base, it turned the litmus a bright blue color. So you might remember that back from January, let's say.